Hello, how's everyone doing today? Wonderful, good, half okay. I'll take it, whichever you got. So I hope we're all doing well. I hope everyone's moving forward on their homework two. Sorry, on their homework three, their trajectory optimization homework. Okay. Again, please get work crack-a-lacking on that. Due Tuesday. Got my dates not mixed up in my brain this time. So anyway, we've got that going. Uh, Also, please keep moving forward on your projects. We'll have a project check-in due at the end of next week. Although there was some request to maybe extend that, I'll have to address that to everyone simultaneously. But today we're here for another coding lecture. We're in my little coding studio, if you will, a room in my house. And we're going to follow up on our coding lecture from last time. So let me just pull up the code from last time so you can see it. Okay, look at that. So we had the sim-pend Lagrange. We were doing this Lagrangian mechanics of a pendulum. Let me see if I can get here. We had our pendulum, and we're using Lagrangian mechanics to come up with the equations of motion for it. And we got a fair bit of the way through the process. And this single pendulum, again, we've seen the single pendulum a lot of times. Okay, we love it in controls for all kinds of reasons. But what I want to do today is get to the double pendulum here. Okay, that's where things get cool, and especially when we're animating it, swinging around and stuff, should be fun. That's what I'm going to get to today, because then we're going to turn this little double pendulum here. We're going to put some torques on it, and sorry, I guess torque on it there, torque on it there. So it's an arm, and we're going to turn it into a robot arm. Probably by the end of next lecture, using operational space control, which we covered on Tuesday. So anyway, so that should be fun. It's like a full service optimal controls course where we're coding all kinds of cool stuff. All right. Fun, fun, fun. Okay. All right. So what I recommend is you pulling up the code if you don't have it already. Again, it's on the canvas if you need to reference it, but it's actually not terribly long. Okay. But what we did is we were scripting using the symbolic toolbox to go through all the Euler-Lagrange equations. So where's our Euler-Lagrange equations? Euler-Lagrange. Here we go. We had our Euler-Lagrange equations for a passive system with no external, no non-conservative forces there. And we set up our Lagrangian, which is L is equal to T minus V right there. Okay, which was our kinetic energy T, our potential energy V. We just summed up all of our kinetic and potential energies. And we even had a fancy way of computing it. We even we did a V dot V to come up with the V squared for our potential energy terms. It's a nice extensible way to do that for 2 and even 3 dimensions. Okay, and we had this fancy way of grabbing the height for MGH, etc. There's our Lagrangian, a logger, our Lagrangian. And look what we did. We did this DDL, DDDQ, DT. That's that term. We computed our DLDQ, that term, right? And then we put together the Euler-Lagrange equation. And then when we run this code, okay, you can see it's just doing a bunch of symbolic math. And at the end, it says, hey, here's the left-hand side of the Euler-Lagrange equation. What does it look like? Okay. Oh, it looks like this. 49 over 5, that's G, is 9.8. This very precise calculation of 9.8. All right. And then, plus theta double dot is equal to 0. So theta double dot is equal to minus G over L sine theta. So it's the thing that we have derived many a time. It just figured that out on its own, right? And then we said, hey, let's put this into the form where we have some matrix term, our inertial matrix M is times Q double dot is equal to some F, which is all the other terms. Sometimes we call that the bias terms, all right? And that's here. And that's us putting onto the other, basically moving all the terms to the other side. So you multiply it by -1, and then you substitute in wherever there's theta double dots, there are zeros. So basically it's every term that does not have a theta double dot in it, it shows up here. Because in order to get it, we substituted in for wherever there were accelerations, ddq, q double dot, we put in zeros, okay? And we put it on the other side. And that's what we got here. So, in fact, look, m, which is 1 in this case, times theta double dot is equal to minus g over L sine theta, okay? So, all right. So why doesn't everyone take a quick second while we get this going? I might have to actually I apologize. I might have to run and take care of something very quickly. So make sure you have this code all downloaded. I shouldn't be gone more than a minute or two. Just be right back. I'll bring up my be right back waiting screen. Oh, and ignore the 12:30. Ignore that. Thank you for your patience. All right. So let's go back to our code. So now we're still in the coding phase. All right. So we have this M and we have this F. What we want to be able to do is calculate our accelerations for forward dynamics. And we're going to simulate the system. Basically, let's try to simulate the system. In order to simulate the system, we have to get the accelerations. Because, of course, when we talked about simulating the system for forward dynamics, so we're going to simulate, which means we need a state space dynamical model, state space forms, state space dynamics, state space form. Okay. So we're going to want our states, we'll call them x of t. We've done a pendulum enough. We know that our state's going to be theta and theta dot of t. And therefore, x dot of t is going to be equal to theta dot of t, theta double dot of t. Okay. Right. And good news. Theta dot is a state. Theta double dot we have to compute. Now, using m to the minus 1 times f. That's what theta double dot is, right? Q double dot. Q is theta. That's our one coordinate. Q is theta. M to the minus 1 times f. Okay? So we need to be able to do m to the minus 1 times f. And theoretically, m can be a function of q. And f can be a function of q dot, and any incoming torques. We don't have any right now. We'll make that a little bigger so everyone can see a little bigger. Okay. All right. Buddy. My little dog is walking around. He had surgery, so he's bopping around with a cone right now in my office. So hear little bops and bangs. That's him. Hey, buddy. He's doing well. He's doing well. All right. Okay. We've got that. M and F. So in order to use that, we're going to need a dynamic. So let's try to simulate this system. Okay. So let's go back to our code. So in order to simulate this system, okay, this system, okay, we're going to need to use ODE. We're going to use ODE 4.5. And for ODE 4.5, we're going to need a dynamics function. We're going to use ODE 4.5 for our ODE, or ordinary differential equation solver. And that means we're going to need a dynamics function. And we've done this a few times. We said, hey, we have some dynamics function, dynamics, and it needs to take in, and we'll just do this in line. This is actually pretty simple enough. We might be able to do this in line. He's taking t and your current state. I don't use x up above, do I? I do not. Just making sure I haven't already used x. Actually, I can check down the left here. I don't see x on the list of the variables in the workspace. Okay. And it needs to return dx. Okay. And since our first, the derivative of our first state is our second state, theta dot, we just say our derivative of our first state is x2. Okay. Then we need our acceleration, which is theta double dot, right? Which is going to be m to the -1 times f. Now, here's the thing. F, let's look at f and m. Okay. M is just the number 1. Okay. And f is this function. You have to plug in theta. So what we really need is to turn m and f into functions that can take in q dot, dq, and all this stuff right here, and any taus, and m can take in q. So we have to turn m and f into functions where it takes in q, and q is going to be our, it's going to be our angle, right? So we want to turn q. We need to turn m and f into functions where we can plug in the current state. Okay. Well, how can we take these m and f and turn them into functions? This is where I'm going to introduce a really cool command in MATLAB, and most programming languages have things like this. It's a MATLAB function that's called matlabFunction. I'll show you what I mean. Okay. Help MATLAB capital function. I think it'll ignore the capital F if you don't need it. For the help function alone, help MATLAB function converts a symbolic expression to a function handle or a file. Okay? You can create a function file automatically. I'll show you what I mean. I'll do an example. Okay? So I'm going to create a brand new, just to show you how it works out of the context of Lagrangian mechanics. I'm going to clear all my variables. Okay, CLC, clear everything. Okay, I'm going to just create I'm going to create some symbolic variables. Sims. I'm going to create an x and a y. Okay, or just even x. Let's say x. Okay, x. And now I'm going to say that y is equal to 2 times x. Okay? Following me along so far? So if I look at the class of x, it's going to say that x is a symbolic variable, right? Because I made it as a symbolic variable. But y, the class of y, is also a symbolic variable equal to 2x. Okay? So you can take a symbolic variable. So let's say I wanted to create, so right now y is equal to 2 times x. Let's say I wanted to make a MATLAB function where it takes in the variable x and spits out 2 times that variable input. Okay? You can, right? If you say, hey, I want to create a new function, I'm going to call it y function is equal to MATLAB function, and I'm going to give it y, which is equal to 2x, right? Hit enter. All right, yfunc is now a function handle that takes in some variable called x and then spits out x times 2.0. How about that? Let's try it out. Yfunc, my one input is x. Let's just say x is 10. This should tell me 20. There we go. Okay? And this works for lots of variables. Let's say I have something called z, which is equal to 2 times x plus 3 times y squared, let's say. Okay? There you go. Okay, that's now Z is a symbol that has a that you can that takes in X and Y. And so if I were to say, hey, something called ZFunc is equal to matlabFunction Z. Now Z is a function handle. Wait, did I? Oh, I meant to say, wait. Oh, I guess because Y is dependent upon X. It only takes X coming in. All right, okay, here's what we're going to do. I'm going to clear everything again. Sims, I'm going to say X and Y. I'm going to refresh everything to X and Y, and I'm going to say that Z is equal to 2 times X plus 3 times Y squared. Just arbitrary function I made for Z, right? Now if I were to say ZFunc is equal to matlabFunction Z, now Z is a ZFunc is a MATLAB function which takes in 2 variables. What does it need to know? It needs to know X and it needs to know Y. So you would say, hey, ZFunc X comma Y. So if I were to give it in like a 1 and a 2, it should spit out 1 times 2 plus 2 squared times 3. So that's 4 times 3 plus, which is 12, plus 1 is 13. 14, 14 is the plus 2 is 14. Yes. So my math is great. Okay. So you can hopefully start to see how we can use this MATLAB function technique to turn these auto-generated matrices, these auto-generated symbolic matrices and vectors into a function so we can plug in instead Q and Q dot and tau and Q, all right? So it's a really handy function, and we'll use this for more than just the Lagrangian mechanics. We can use it for helping with all kinds of making helper functions for trajectory optimization, so that way you can have a constraint function that's automatically generated. You can do all kinds of really cool stuff, okay? There's a couple there are 2 particularly useful arguments that you can pass into MATLAB function. For one, right now, like ZFunc, when I said ZFunc is equal to MATLAB function Z, it just made a function handle, right? Meaning, so it's just an inline function. So it's stored in memory. There's ZFunc. It's really tiny. You can't really see it in my workspace right there as a function handle. But you can also make a function file. Watch this. I'm going to take that same command, ZFunc, okay, and I'm going to say, all right, yes, I'm going to do MATLAB function. I don't even need it to make it equal to ZFunc. I just want to make a function file called ZFunc that has those inputs. So I'm going to say Z, comma, I want to make a file. So open apostrophe file, then the name of the file, okay, that I want to call it. And I want to call it ZFunc, or Z underscore FUNC for function, okay? And this should make a function file in my current directory called zfunc.m. All right, so I'm going to hit enter. All right, it says it did something. Oh, look, up in my upper left-hand corner, I'm going to double-click on this new function that showed up. Hey, look, automatically, new function called zfunc. This function was generated by the Symbolic Math Toolbox. It tells you exactly when. All right, and that's what the function is. So now I can use that function like as if it's a function file. So I could say zfunc 1 and 2, and that'll tell me 14, right? Because that's now a function file. Really powerful stuff. Okay? All right. Now I don't need that anymore. I'm going to delete that function. I don't need that anymore in my life. That was just for, we will enjoy the short time we had with that zfunc that we auto-generated. All right. So we got to do the same thing here. Oh, and one other thing. Automatically, if you do the zfunc thing, I'll show you just it'll automatically in its own order give you an order of like these variables, okay, X then Y, and MATLAB will determine what order the inputs are. But if we have a function that is like taking in a bunch of variables, it's like if we had a lot of Q's for a lot of coordinates, it might be helpful to decide on our own what the ordering of the variables are, and if they're in a vector. So one thing we can do is we can tell it specifically the variables we want as inputs. So we could say MATLAB. So we could say MATLAB function instead of a file. We could also say, let's also say we want the variables vars, and we put them in a cell array. I want them to be, I think we say x then y. Make sure I get this right. Yes, okay. So you can give it characters saying these are what I want my inputs to be in that order. And so now I can go into my zfunc that I just made, the file. It's x then y. But if I wanted to be in a different order, I think I could say y then x. Y then x. There we go. Right there. So that gives us some control of how we're going to actually set what the inputs are. Because what we're going to want, in addition to just getting the order right, we don't want it to say, hey, put in theta 1, then theta 2, then tau 1. You know, no, what we want to be able to send in is a vector of q's. So we'll say, hey, we want to send in our first input to be a vector of q's, our second input to be a vector of dq's. We'll be able to set that using the vars argument here. Okay, so that's how awesome the MATLAB, the MATLAB function generator is in the symbolic toolbox. It's pretty cool. So we're going to use that for our own purposes. But there's going to be a couple of wrinkles. It's going to make our life a little bit hard, but we will fix, okay? So you might say, oh, this is great. This is awesome. Let me rerun this my script, my sim pen Lagrange. What did I screw something up? Did I get rid of something? Line 55. Oh, okay. Sorry. Yeah, this whole code right now is wrong. We're gonna comment it out. That doesn't actually do anything yet. This is showing that we're gonna need functions in here. That's all I'm showing. Okay. So let's set that here. Do not disturb. Good. Awesome. So let's rerun this code now that I've commented out that dynamics function that currently doesn't work. Okay, so what we want to be able to do is turn this f and this m here into functions, all right? The only challenge here, and this is what the spoiler, is that currently these are not symbolic variables. These are now symbolic functions because they're functions of time. So we're going to need to have a way to make these non-functions of time, and I have a way to do that. There might be better ways to do it, but it's just a little tricky. That's what we're going to run into. So, so for instance, if I say, hey, I want to do a MATLAB function using f, okay? And when it says, that says great. That's awesome. However, it says the only input to it is time. Not, see, it's within the at symbol is time. What we want is an input of theta. Okay? So how can we get that to be an input of theta? Let's try using the vars command. Let's say vars, we want our input to just be theta of t. Let's see if that works. Nope, doesn't like theta of t. Let's just try theta. And it must include t, apparently. And that's the other problem. It's going to ask for t. All right. You give it theta, but it also asks for time. We just want to be able to put in theta, not the current time. So what we're going to need to do is we're going to have to remake these M and F matrices such that they are no longer time dependent. Okay? It just requires a few substitutions, but it's something we can absolutely do. Okay? So let's do that. It's going to be a little messy, but we will. So what we're going to do is right when we have these left-hand side, right-hand side things happening, okay? Let's look at EL LHS. Euler Lagrange, left-hand side. Here we have a couple of things. You have this theta of t, and you have their diff theta of tt. That's theta double dot. What I want to do is I want to replace this with a symbol that's just called dd theta. And that's it. Okay? And I want to replace this with just a symbol called theta. Okay? But theta is, or th, right? Th is already taken, though. So I'm just going to give a new version of th that looks the same. but I'm just put a little underscore after it. So it's a theta, but the only difference is it's not dependent upon time. And that's going to allow us to use the MATLAB function, the MATLAB function generator to generate functions where theta is as an input. Okay. So for instance, if I create theta, right, I could do a substitution of f when wherever I saw theta, I want to replace it with theta underscore, right? I could do that, right? Sure enough, I did. All right, for f, it replaced sine of theta, theta underscore. The only challenge, though, is it also replaced this, and then it took a time derivative of something that was no longer time dependent and made it 0. Okay, so we killed the theta double dot. Oh, no. So here's what we have to do. Thankfully, we still have f. It's still in memory. Wait, did I? No. Oh, no, ELLHS. I'm sorry. I did the wrong thing. I apologize. So ELLH, we want to do that with ELLHS, not F. Sorry. So if I go to if I want to substitute into EL, Euler-Lagrange, left-hand side, where there was once theta, I want theta underscore, my new version of theta that's no longer dependent on time. If I did that, okay, same problem. Okay, we have this theta, and it got rid of this dd theta. Where did that go? Okay, so what we're going to want to do instead is we want to, so we still have ELLHS. It's still there. We didn't overwrite it. We just said what would happen if we substituted it in. Okay, we first want to substitute the derivatives. Okay, that whenever we see the second order derivative, we replace it with like a dd theta. Okay, and whenever we see, then we say whenever we see a first derivative, we want to substitute in a d theta. Whenever we see a 0th order derivative, we substitute in a theta. Okay, show you what I mean. So let's so what's going to happen is I'm going to say EL LH. So I'm going to create a new symbols. I'm going to create symbols. I'm going to create not just theta underscore, which we already did, also d theta underscore, a non-time dependent d theta, theta dot, the velocity, and dd theta underscore. Okay. Now I can substitute in, starting with the highest order derivative, I want to replace this with that. Okay, it's the second derivative with dd theta. Again, a little tricky. This is the trickiest part from a coding standpoint of everything that we're doing here. So we're substituting where we previously had the derivative of theta with respect to time and time. Wherever you saw that, replace that with dd theta underscore. There it is. Make it a little larger so you can see everything that was written. Okay, that was replaced with that. See that? Then you could replace the single derivative. I just hit up. I could do the single derivative, which doesn't exist in this line of code, but if it did, you could replace it there. Etc. Okay? So we're going to write these into lines of code here. All right? So what I'm going to do is right where I have this ELLHS, we're going to substitute non-time dependent versions of our coordinates and derivatives. Okay? That's what we're going to do. So we're going to create our symbols. We're going to create theta underscore, d theta underscore, and dd theta underscore. And we're going to create a vector version of that where q underscore is a vector with just theta underscore. And dq underscore is just a vector with all of our velocities, now not time dependent, d theta underscore. And ddq underscore is a vector with just our dd theta underscore, which is our only coordinate is theta. But this will be helpful when we have multiple coordinates soon when we do the double pendulum. Okay, so now we have those coordinates. Now I'm going to say ELLHS is equal to the substitution of EL LHS. So now it's going to, it's now going to do a substitution and store it back in LHS, right? Wherever it saw a DDQ, which was the actual accelerations, right? Yeah, we have the accelerations up there, DDQ, which are the time-dependent versions. So replace them, please, with DDQ underscore. Okay. Then I'm going to copy this, replace, you have 3 versions of this. Then I'm going to say wherever there was DQ, I'm going to replace it with DQ underscore, the non-time dependent version. And then wherever there was Q, I'm going to replace it with Q underscore, the non-time dependent version. Okay? Now I'm going to run this, see if this all works. Okay. Now let's type in EL LHS. And sure enough, look at that. It's got a non-time dependent version of DD theta and a non-time dependent version of theta. That's great. There's one last tricky bit, and this is just a symbolic toolbox annoyance, okay? I'm open to other ways around this. Notice that if I look when I type out EL LHS, it says the EL LHS, the Euler-Lagrange left-hand side, it's still dependent on time. That's because when it was created, it was dependent on time. And yes, we individually removed all the things that are no longer dependent upon time, but it doesn't know that. So it thinks that there is a time-dependent LHS, right? So it's still time dependent. So what we're going to do at the very last step is we're going to say, hey, our EL LHS underscore, which is a new non-time dependent, LHS, left-hand side, is you could say, hey, I just want it to be just the first element of this vector of left-hand sides, right? I could say, oh, EL is equal to just EL LHS without the underscore, so time dependent. Oh, I want the first one. But again, we run into a trap. Because when we say 1, we put in that 1, you know what it thinks it means? It thinks it means we're substituting 1 into there, okay? Now, does that work? We'll see. Because technically there's no more time anymore, so it might work out okay. So let's see. What happens if we say, I don't know what I just did. I hit something. It's doing crazy. It's running the code over and over again. Anyway. So let's look at EL LHS underscore. Voila. Technically, let's put in a 0 here. It still technically works. We got rid of all the times. There we go. There you go. That worked. So inputs and arbitrary time as all times have been removed if you did it right. Okay? Now we have EL LHS underscore. Okay? So now if we do our Jacobian using EL LHS underscore and using DDQ underscore for non-time dependent versions, and same thing with EL LHS underscore and DDQ underscore and size of DDQ underscore, even though it's the same size. Let's look at what F and M come out. Okay, now if we look at M and we look at F, they are no longer dependent upon time. And all of their variables are non-time dependent variables. Okay? Everyone follow that? Anyone need to see any of those lines again? We just went to the left-hand side. We substituted where there were prior. Substitute. In non-time dependent versions of the variables. Right? This allows us to make MATLAB functions with inputs of Q and DQ instead of T. All right? So now we can do MATLAB functions, right? So I could say, hey, I have a function called mfunc. All right? and it's a MATLAB function, and it's of M, and if there's any Q underscores in there, okay, so we have to, oh, and if the variable inputs, the vars, the only variables we care about are Q underscore, and I'm putting it into a cell array. And this is just a way that if every, and that's what this curly brace is, a cell array in MATLAB. So if we wanted Q and then DQ underscore, which we don't for a mass matrix, as we all know, M is only ever dependent upon Q and not DQ, right there. Okay. But if you want, this would be a vector of all your Q's and then DQs if you wanted it, which we'll need for the F. Okay. But there we go. That's a MATLAB function, M dependent upon Q, right? Now, let's do an F func for the bias term. That's this thing right here. All right, is equal to MATLAB function F vars, and it's going to take in Q and underscore and DQ underscore. We don't have any taus yet, but for later. Okay, let's make sure this all runs okay. Sure enough, it seems to run. M func here takes in theta and just spits out 1. Right now, it's not even dependent upon theta, but it'll still take it in. Okay, that's good. That's the power of doing this, having this little vars input argument, right? Then for our F func, it takes in theta and d theta. Sine of theta times basically G minus G over L. Okay? Nifty, neato, awesome. This is pretty cool. And you might say, or you might be thinking, wow, I wish I could just write G over L sine theta like we did a bunch of times in this course already. This will expand so much better for when we're doing more complicated multi-body systems like the double pendulum, okay? Which I want to get to. Excuse me. All right, so now we're actually close to using these dynamics. So let's go back to these dynamics. Now, M requires Q going in. Q is our position. That's our first state, x1, right? And F is dependent upon our position, x1, and our velocity, which is our second state, x2. And we don't need the tau, right? Yeah, we're good. That's our acceleration. These are our position and acceleration. So those are our dynamics. So now we can, if we have an x0, which is an initial state, we're now able to simulate initial state x0. Let's start it at pi over 4. That's 45 degrees from the vertical and at 0 velocity. Okay, we've done this many a time. Time span. Let's simulate it for 5 seconds from 0 to 5. Okay. Time span. Now we can run ODE 45. We need our time out and our state out, x out. Okay. We're going to plug it into ODE 45. And our function handle is dynamics, we called it. We have our time span. I don't like the underscore. Get rid of the underscore. Just T-span. Just T-span. Got rid of the underscore. T-span. All right. Then we need our initial state x0. We'll forego the options right now. Semicolon. So this is, simulates our dynamics. Nice. Now we're going to plot our pendulum swing. So when we need our angles, we'll call our theta plot. Well, those are going to be the entire first column because it's our first state of x out. So x out every single row, which is colon, first column. There we go. We need our time. Our t out is our t plot, right? So now we can plot our t out versus our theta plot, and we'll just make it a black line. Okay, and let's label it time on the x-axis in seconds. I'm so good at typing. Time in seconds, and y label. Let's do an angle in radians. Okay, and let's plot it. What happens? What did I screw up? What did I screw up? All right, index position 2. It didn't like something I was doing. Colon operator as Integer operands are okay. So if I'm giving it a non-integer. Oh, okay. I said m instead of mfunc. That's the problem. Okay, I created functions mfunc and it's still using m here. That's the so we had to say mfunc. That was the whole point of making those of those functions. Mfunc and ffunc. That's what I screwed up. Okay, now try running it. Okay, it looks like it's running some kind of simulation. Taking a hot minute here to run. Any day now, MATLAB. Oh, look at that. One could argue that looks like a swinging pendulum, my friends. Anybody else getting that? Anyone else getting that? So it's generating the equations of motion for this pendulum. Give me a thumbs up if you're getting that. Okay. All right. Nifty neato. All right. Single pendulum. Again, only so exciting. Even though it is automatically generating those dynamics, let's do the double pendulum. Let's dive right in. I got an error in that you're investigating. Okay. It's only 86 lines. Can I put this into code into? Yeah, it's too long. Okay. All right. All right. Tell you what, I'll be kind. Give me a quick second. I think I might be able to make this work where in the chat I can make this happen. Watch this. I'm pasting it into the Zoom chat. In case you need something to go off of and compare in MATLAB. This will have everything except the plotting. This has everything but the plotting. Okay? Put that into your chat. All right, so let's do, I'm going to march on forward. I'm going to do a double pendulum. Okay? So for this, let's get this set up back on our board here. Double pendulum. We use the same procedure. And the equations will become much more complicated, but we don't have to worry about those. MATLAB Symbolic Toolbox takes care of it, right? So, double pendulum. This will be the gateway to our robot arm, our in-plane robot arm, okay? And if you're interested in doing more advanced dynamic stuff, I'll be teaching advanced dynamics in the fall. I'll be doing something similar to this. Assuming I can get the YouTube streaming working kind of like I have this semester, I'll just live stream all those lectures too. Double pendulum. Okay, so we are going to define our double pendulum in a somewhat similar way. We're going to have some mass 1 and some L1, and we're going to define some theta 1 from the vertical. I think we all understand this is of time, okay? All right. And then we're going to define a relative angle relative to the other angle, theta 2, of length L2 with another mass 2 at the end, okay? We're going to assume these are infinitely thin rods connecting. We can add rotational inertia. That's something we can do. We're going to add, of course, have it under gravity. That's where all the fun comes from. And we could add torques later. Okay, we'll just get the double pendulum going. See if we can blitz through this. Okay. One thing it's helpful to do to start with is to draw vectors. We'll make them in red. R1 and R2 to each of our masses. That'll help us compute our energies later, okay? So let's set this up. So R1, okay, going to be a vector. It's going to be in the horizontal direction, so let's say X and Y. In the Cartesian, we call that the Cartesian plane, you know, the Cartesian coordinates, X and Y here. In the X direction is going to be L1 sine of theta 1. And then it's going to be minus L1 cosine of theta 1. We've done this a bunch of times. Then R2 is going to be equal to R1 plus this vector here, right? Okay, where this angle is going to be theta 1 plus theta 2. So it's going to be R1 plus L2 sine of theta 1 plus theta 2. That's the first part of that vector, comma, minus L2 cosine of theta 1 plus theta 2. Right? Those are our two vectors, right? And we can just do a little vector addition that helps us out. We can do that all in the symbolic toolbox too, so that's going to be helpful, right? So I'm going to be making a, we can make a new script from scratch. We're also going to need our generalized coordinates. Okay, what are our generalized coordinates? Our generalized coordinates, Q, we have two generalized coordinates. They are theta 1 and theta 2. Okay, so let's start with that. I'm going to go back to our code. Let's do a whole new script from scratch. Let's call it sim double pendulum .m. Sim double pendulum .m. I'm saving it. It's by Christian Kubicki and all my friends. This day, which is 2026 0408 of the Common Era. Okay, we're going to simulate. So we're going to derive the equations of motion of a double pendulum. Now, all these tricks and tools that we use for MATLAB functions being generated automatically to create files and such, that is going to be so handy for operational space control as well. I'm telling you right off the bat. Okay. Yeah, we're definitely not getting there today. Let's see if we can get, so let's clear everything first. And simulate. Okay, clear everything. Clearing all the variables, closing all the plots, clearing the works, the command window. Okay, run it, clear everything. Okay, so now we're going to define our symbols. Okay, so we're going to first define our symbols time. Okay, then we're going to define our symbols theta 1, which is dependent upon time, and theta 2, which is dependent on time. Okay, let's define our parameters. Okay, L1, L2, let's make them equal to 1. Let's make M1, let's make that equal to 1, and let's make M2 equal to 2. We can mess around with those later. That's the beauty of it, is if we ever change one of these parameters, we can, boom, change the equations, and it'll regenerate and resimulate. It's pretty cool. All right. Moving on. So we have our parameters. Oh, and G. We need G is equal to 9.8. I trust we know what those mean without the comments there. We'll just go with that. All right. So we have those. Let's define our generalized coordinate vectors. So Q, it's a generalized coordinate vector. We have it right there. It's theta 1 and theta 2. Theta 1, semicolon, theta 2. I'm going to run it without a semicolon with at the end so we can see that Q is in fact a vector with theta 1 and theta 2. dq is going to be the time derivative of Q with respect to time, you know? And then ddq is going to be the time derivative of Q with respect to time and time again. Run those. Make that bigger so you can see. Sure enough, you got theta 1, theta 2. dq is the time derivative, and then the double derivative, okay? Nice. We've got that. Now let's go back to where we defined our vectors to our masses. That's going to be helpful for defining our energies, okay? All right, so define the vectors to our masses. in Cartesian space. Cartesian space, again, that means like X and Y and Z as we traditionally know it. It's helpful. So R1, we've said, is a vector. Right here, it's this, all this stuff, right? So it's going to be the first element. It's going to be L1 sine theta. So L1 times sine of theta 1, to be clear. Semicolon for the vector. Okay, minus L1 cosine theta 1 minus L1 times cosine of theta 1. Make sure that works. It's I keep getting running the check to make sure I didn't make any errors right there. That looks right. Okay. Now R2 is equal to R1 right there plus L2 sine of theta 1 plus theta 2. L2 times sine of theta 1 plus theta 2. Semicolon. Oh, and by the way, this also should be a vector, so I need a square vector right there. And so then we have minus L2 times cosine of the quantity theta 1 plus theta 2. All right, end bracket. Let's run it, see if it still makes sense. And sure enough, looks like it makes sense here. That's great. Now we're getting into the Lagrangian mechanics part. So we have to have our L is equal to T minus V, which means we need our potential energy. That'll be pretty easy using just these positions here. But for T, we're going to need the velocities, right? So what we can do is we can get the velocities. So we can say, here's our mass velocities in Cartesian space. All right, so dr1 is going to be the time derivative of r1 with respect to time. And dr2 is equal to the time derivative of r2 with respect to time. Let's run that, see if it makes a proper time derivative. And sure enough, it does, and in fact has the chain rule involved. Isn't that nice? Isn't that nifty? Multiply by the time derivative, okay? And then you look how quickly things get a little nastier when you get out to more distal end, further out on the double pendulum. dr2 becomes more and more complicated. You'll notice the triple pendulum will become even more complicated, right? Nifty, right? Okay, mass velocities in Cartesian space. That's great. We have those. So now let's actually get our V's. It's going to be equal to M1GH1 plus M2GH2. That a little bigger so you can see. So those are our potential energies. So let's say here's our potential energies. And you can break this out and you can say, hey, V1, that is the potential energy of mass 1. That's going to be M1 times G times H1. Now recall that that our H1 is going to be the second element of R1. And the cool way to get that is we multiply it by 0 and 1 using matrix multiplication. And this will say, hey, I want 0 of the first element plus 1 times the second element. And so this works because otherwise R1, you'll notice, is time dependent. So if you said R1 and you try to grab index 1, it wouldn't work. Okay. All right. And we do the same thing and copy this for potential energies for M2 and R2 for V2. And so you can say all your potential energy is equal to V1 plus V2. Look at V. There we go. There's V. There's an expression for it, right? All right, now we need our kinetic energies. Following so far? I mean, we're just going through the same procedure. But but the procedure is, look, it's kind of simple. Let's find where all the masses are. Find the energies, right? What's T1? Well, it's going to be 1/2 mv squared. So, 0.5 times mv squared. So M1 times, and again, the way of doing v squared is we would say v dot v, okay? And that's an inner product. And the way we talked about last time, so we would say we want dr1, which is the velocity, and we multiply its transpose by itself. And that would, in essence, that would give you, this would give you, Vx, Vy, Vx, Vy. What does that equal to? That's equal to Vx squared plus Vy squared. And that's what we want, right? Because it's the velocity would be the square root, and then you square it, okay? And in order to do that transpose, you want to do a dot transpose. Otherwise, it will do a complex conjugate. Okay, so we want to do a dot transpose there. That's the only trick. Times dr1. That's T1. Copy it for T2. T2, second kinetic energy of the second mass, is equal to 1/2 mv squared, 1/2 m2, dr2 transposed times dr2. That's the v squared, right? Run that. There we go. Look at this. All these terms here. Look, it's getting a little large. Do I see any sine squared or cosine squared? No, not particularly. Maybe, maybe not. I don't know if it needs to be simplified or not. Okay, we'll find out. But regardless, when you got to add these kinetic energies together, T is equal to T1 plus T2. All right, now we got to compute our Lagrangian. And our Lagrangian, as we know, is equal to T minus V. So our Lagrangian is equal to T minus V. What's our Lagrangian look like? Oh, looking pretty nasty. Look at all that. It's getting pretty big, okay? Now we got to start taking these derivatives, okay? So for the Euler-Lagrange equation. Now recall the Euler-Lagrange equation. And again, we have no non-conservative forces in the system. We will add those at the next lecture, okay? When we get to the actual control side, which are non-conservative forces we're adding through the torques we're applying. So it's going to be d dt partial L partial Q dot minus partial L partial Q is equal to 0. So let's start with this partial L partial Q term right there. Call that dl underscore dq. And because we are taking the derivative with respect to q, and q is now a vector, as all of you no doubt understand, we have to take the gradient now of our Lagrangian with respect to q. So you can look at what that looks like. All right, dl dq. Look at that. Look at that monster. Now you'll notice that it has two elements in a column vector, right? It's a gradient. Look at that. Boom, boom, boom. Making sense? I'm glad. Now we need to do this term, which will break down into doing dl ddq first. So let's do a dl ddq. Is going to be the gradient of the Lagrangian with respect to dq. dq. Does that work? Sure enough, it does. Getting nastier. Getting nastier all the time. All right. Now we need to take the time derivative of that thing we just calculated. We need to take the time derivative. So we're going to say ddl d dq dt is equal to the time derivative. It's only with respect to one variable. So we're going to say of dl underscore ddq with respect to time. Brace yourselves. Let's take a look at this. Getting big, right? Anyone else getting this? Glad I'm not doing that by hand, right? Okay. Nifty. So now we got our Euler-Lagrange left-hand side. Right? And that's going to be this term minus this term. So we'll say that EL LHS is equal to DDL DDQ DT minus DL capital L DQ. Holy moly. Believe me, it gets worse for lots of systems, okay? Let's just do a quick simplification, see if that makes it any easier for us. So we'll see EL LHS is equal to a simplified version of itself. See if it can come up with anything that can simplify ELLHS. There you go. Oh, not nearly as bad. Hey, look, we simplified. Not too bad. All right. Now we got to get to the point where we want to do we have all these time dependencies that we had before, this trick we did before. Let's try to get rid of those time dependencies, okay? So let's eliminate the time dependencies. Okay? So what we're going to have to do is going to create some non-time dependent versions of all these variables. So we have sims theta1 underscore, theta2 underscore, d theta1 underscore. Actually, here's what we'll do. We'll do this in order of theta ones first. So d theta1 underscore, dd theta1 underscore. Okay? I'm going to repeat that. I'm going to do theta2, theta2, theta2. All right? So we got these non-time dependent versions of theta1 and theta2. All right? And now we want to create a q underscore, which is just theta1 underscore, semicolon, theta2 underscore. It's a vector of our generalized coordinates. I'm going to copy that. I'm going to make a dq. So dq, d theta1, d theta2. ddq, dd theta1, dd theta2. All right, these are just non-time dependent versions of our coordinates. Okay? That's helpful because now we can do a substitution, right? We can say we want to substitute. We want to say our left-hand side, ELLHS, we're going to substitute into ELLHS where there were once DDQs. We want now DDQ underscore, the non-time dependent versions. I'm going to copy that. I'm going to repeat that, followed with DQ, and then finally Q. And you want to start with the highest order derivatives first. Otherwise, you are going to be substituting in stuff inside of the derivatives and then taking the derivatives of a constant. You're going to be zeroing out a lot of things, okay? So we'll do it in that order. So looking at ELLHS after all these processes, sure enough, here's ELLHS. I'm looking through. I don't see any times anywhere in here. Not too bad, okay? The only thing is it still thinks it's dependent upon time. So we're going to do a quick trick and say ELLHS underscore. It's a non-time dependent version of ELLHS. It's just equal to ELLHS, where we plug in an arbitrary time for t. Plug in an arbitrary time. And if I run that, ELLHS should be a symbolic variable that has no time dependence. Look at that. Okay? Indeed it does. Great. Okay, now, let's separate the inertial terms, M, from the non-inertial terms, F. Okay? So we can do that pretty easily because on the left-hand side has all of our terms. And so if we were to say, hey, M is now the Jacobian, so it's going to grab every term that is multiplied by an acceleration. It's going to grab it and throw it into the matrix, a square matrix in this case. It's going to always be a square matrix. Take the derivative of ELLHS underscore with respect to DDQ underscore. Okay, our accelerations. This will pull out all of those, all the terms that are multiplied. Oh, there you go. Look at that. Those are the inertial terms. There's the M matrix. Okay. Now let's go to F. That's going to be every term that isn't multiplied by DDQ. So what we'd say, hey, wherever there was on the EL left-hand side, wherever you saw an acceleration, substitute in a 0. Okay? We want zeros of the size of DDQ underscore. That's going to leave all of our terms that are not that are not accelerations, okay, or multiplied by an acceleration, right? And we're going to put it on the other side of the equation because again, what do we want? We want m of q times q double dot is equal to some f of q dot, right? So it means we got to put it on the other side. So we got to multiply it by -1. -1 times that. Okay. The only ELHS underscore. Don't forget the underscore. Also, you'll get a time-dependent version. Okay. Sure enough, there's f. That's a little more complicated. Okay. Nifty. Doing okay so far, right? So we now have our m and our f. Let's turn them into functions that we can then use for simulation. Okay. So let's create functions for simulation. So we're going to create an m_func. M_func is going to be a MATLAB function. All right. So we turn m, our inertial matrix, into a MATLAB function. And what are the inputs? What are our variables? Okay. So it's comma vars. And in a cell array, we want to indicate that we want to send in q underscore. And that's it. That's all we should need, right? Then we need f_func. Okay. MATLAB function. We need to say f. And where, for our variable inputs, we need not just q, we need q and q dot there, right? So vars, comma, open curly brace, q, comma, dq underscore. See if that works. Well, it gave me something. Didn't throw an error. There's f_func. There's m_func. Great. And you can make this into a file if you wanted, but we don't even need a file. Okay, this is actually pretty simple. All right. So now, we're ready to simulate our double pendulum. We're making good time. All right. So we can finish in the next 5 minutes here. So we need our dynamics, right? Okay. So we need our dynamics function for ODE 4.5. Our dynamics, we're going to take in time and our current state x. Now, for our state, we'll just write over here pretty clearly our state x of t. We're going to have a position and velocity for each of our variables. If you looked at our dynamics, you would see, and you were to do our whole procedure, you would count up the fact that we're going to need 4 states. We're going to need theta 1, theta 1 dot, theta 2, theta 2 dot. Okay, and those are, of course, dependent upon time. That's our state vector. Makes sense? So that's going to be our state vector we're working with. So, it needs to return the derivatives of all 4 of those states, okay? All right? So, the derivative of theta 1 is theta 1 dot, which is the second state, right? x2, semicolon, right? What I'm going to do, I'm going to switch these around to make this a little easier. Apologies. This is going to make our lives a little easier in code. There's no reason we can't change the order of the states. Okay, there's no reason. We get to choose the order, right? We're going to make theta 1 dot and theta 2 dot. We're going to put the velocities at the end. All right, this is going to help us out ever so slightly. Okay? Which now means that the derivative of our first state, theta 1, is theta 1 dot, which is our third state, right? So we're going to return x3. And then the derivative of our second state, theta 2, is theta 2 dot, which is our fourth state, x4. Okay? All right. Then that leaves the derivatives here, which are accelerations. Good news, friends. That's theta 1 double dot and theta 2 double dot of t, otherwise known as q double dot of t, which we now know is m to the -1 times f. Okay? Now, of course, m is dependent upon q, and f is dependent upon q and q dot. We're extremely close. Oh my goodness. So we're going to get this done. We're going to get this done. So that means that the result of this, so it's going to be m the minus 1 times f. So let's say m func, we'll leave the open close for now. We'll finish it to the minus 1 times f underscore func, right? What we need here, we need q. Well, q, as we know, is equal to theta 1 and theta 2, which are our first two states, right? So we could say q, which is 1 colon, which is x, it's just x1 colon 2. Make sure that if I do just do a quick check here. So if x is equal to zeros, make sure the shape of this is right here. So x1 comma 2, beautiful, great. Okay, so it's going to be just x1 comma 2, 1 colon 2. The first two elements of x are our two q's, right? Then for f, we want to put in q. Q here is x1 is x1 and 2. And our velocities are comma x, 3, and 4. The 3 and 4. 3 and 4 are our velocities. Let's make sure it doesn't create an error when I run that. Cool, good. Ooh, good. All right, those are our dynamics. Let's define our initial state, x0. Our initial position for the first pendulum, we're going to make it 0. We're going to make it vertical, and then the second one, no, I know what we're going to do. We're going to do pi over 4, semicolon, pi over 4. So it's going to be an elbow bend. Boom, boom. That's what it's going to do. All right. And semicolon 0, 0. Initial velocities are 0. Okay. Our time span, we're going to go for 5 seconds from 0 to 5. Okay. We're here. We're here, friends. So then we're just going to store t out and x out and simulate it. ODE 45. We have our dynamics function. Done. We have our time span. Done. We have our x0. Done. Store it. I'm going to plot both angles on the same plot. So let's see. I'm going to say plot. I'm going to do a hold on. I'm going to plot t out and our first angle, which is going to be x out colon comma 1. That's the entire first state. I'm going to make it red. And then for our second angle, tx, x out, that's going to be our second state. That's going to be colon comma 2. All right, and make that blue. Okay, I'm just going to say y label angles and x label time in second. And this is in radians. Okay, does this work? Let's run it and find out. Holy bananas. That looks like a double pendulum swing to me. We're not animating it yet. We just get this out of your way so people can catch the code. All right? This is probably the money maker right there. Let me put that into the chat. We did it. We simulated a double pendulum, my friends. Okay? Oh my goodness. And it's going to look so cool when we animate it. We did it. From scratch. It delivered on the double pendulum. Look, this becomes chaos, my friends. It becomes chaos. All right. And I'll show you. We're done. I'm just going to take a minute to just say, hey, look what happens if, let's say, we change this to the second mass to 0.5. It should start doing crazy things. It should start moving around in weird ways. Now, here we go. No, it's not as crazy as I thought. I think it's just starting to do like a swing thing. Okay. All right. Let's see. 0.1, same deal. I'll change it back to 0.2. I'm just messing around. Oh, look, that second mass is just flopping around like crazy. It's doing multiple laps, doing rotations. So anyway, hard to appreciate with the animation without the animation, but coming soon. All right, that's what we got for today. Hopefully that was intriguing, my friends. From scratch. Look, it did all of the dynamics for us. And guess what? You could do this for a triple pendulum, or a quadruple pendulum, or a quintuple pendulum. Eventually, MATLAB starts to choke on the math, but it's not that bad. for now. Okay, that's what we got. Thanks, folks. Hope you enjoyed. I enjoyed. Look at that. Double pendulum dynamics. All right, friends. Thanks so much. Take care.